In this section, you just only have one objective: approximate a zero of a function using Newton's method. The technique for approximating the real zeros of a function is called Newton's method, and it uses tangent line to approximate the graph of the function near its x-intercepts. To see how Newton's method works, consider a function f that is continuous on the closed interval ab and differentiable on the open interval ab. If fa and fb differ in sign, then by the intermediate value theorem, f must have at least one zero in the interval ab. To estimate this zero, you choose x as x1. The x1 is the first estimation. Look at the figure here. Newton's method is based on the assumption that the graph of f and the tangent line at x1, fx1 both crosses the x-axis at about the same point. Because you can easily calculate the x-intercept for this tangent line, you can use it as a second, and usually better, estimate of the zero of f. The tangent line passes through the point x1, fx1 with a slope of f prime x1. In point slope form, the equation of the tangent line is y minus fx1 equal to f prime x1 times x minus x1. And we move negative fx1 to right side. And we let y equal to 0 and solve for x. Produces x equal to x1 minus fx1 over f prime x1. So, from the initial estimate x1, you obtain a new estimate. And for this new estimate, we can name it as x2. So look at the curve here. First, we estimate the s1 and we get the tangent line. The tangent line crosses x-axis and we let y equal to 0, so we get the x2. You can improve on x2 and calculate yet a third estimate. Repeated application of this process is called Newton's method. Let fc equal to 0, where f is differentiable on an open interval containing c. Then, to approximate c, use dash steps. Make an initial estimate x1 that is close to c. You can contractible then sketch the graph and determine the interval. Determine a new approximation based on this formula. When the modulus of xn minus xn plus 1 is within the desired accuracy, let xn plus 1 serve as the final approximation. Otherwise, return to step 2 and calculate a new approximation. Each successive application of this procedure is called an iteration. Look at this first example. Calculate 3 iterations of Newton's method to approximate a zero of fx equal to x squared minus 2. Use x1 equal to 1 as the initial guess. Because fx equal to x squared minus 2, you have f prime x equal to 2x. And the iterative process is given by the formula. You can contract a table to complete the calculation. Look at this one. For n equal to 1, we have x1, where the x1 is given by the question. And we substitute this x1, the value is 1, substitute into the original function. We have negative 1. And this value also substitute into the first derivative function. So we have 2. And we take negative 1 divided by 2. So we have negative 0.5. And we use the formula. For n equal to 1, we have x1 minus fx1 over f prime x1. The x1 is 1. The fx1 is negative 1. The f prime x1 is 2. And actually the value here is negative 0.5. So we have 1.5. This 1.5 we drag to here. This value we call as a new value. So we name it as x2. So when equal to 2, x2 equal to 1.5 is new value. And we substitute this new value x2 into original function. So we have fx2 equal to 0.25. And we also substitute 1.5 into first derivative function. So we obtain f prime x2 equal to 3. And we take fx2 divided by f prime x2. We have a value is 0.0833. And we plug it into the formula. x2 minus fx2 over f prime x2. And this value is new value. So it's x3. So we drag to here. So n equal to 3, meaning that is x3. And this value substitute into the original function to get the fx3, and substitute into the first derivative function to get the f prime x3. And the fx3 divided by f prime x3 is equal to 0.002451. And we substitute into the formula. So we have 1.414216. And this value is a new value. It's a x4. And we stop here because we have conducted 3 iterations. Of course, in this case, you know that the 2 zeros of the functions are plus minus radical 2. To 6 decimal places, radical 2 is equal to 1.414214. So, after only 3 iterations of Newton's method, you have obtained an approximation that is within 0.000002 of an actual root. The first iterations of this process is shown in figure below. Look at the curve x squared minus 2. The curve crosses at this point.